Hello everyone, my name is Roger Juan from Computer Science and Information Engineering Department of National Taiwan University. Today I'm going to give a short survey on ensemble learning. In particular, I'm going to focus on how to use decision trees for ensemble learning. Play mode. So hello everyone, my name is Roger Juan. I'm from the Computer Science and Information Engineering Department of National Taiwan University. Today is my honor to give a short introduction to ensemble learning. And in particular, I'm going to focus using decision trees or regression trees for ensemble learning. So here, this is the outline of the talk. So first, I'm give you a brief introduction to ensemble learning. Then there are two types of ensemble learning. The first one is bagging. The second one is boosting. And in particular, I'm going to focus on how to use decision trees for bagging and boosting. If you are using these decision trees for bagging, then turn out you end up with the so-called random forest. On the other hand, for boosting, I'm going to introduce gradient boosting. And if you are using this decision tree for gradient boosting, there's the so-called extreme gradient boosting or XGBoost. This is a very useful and have been many winners for machine learning competition. And finally, I'll give a short conclusion about this talk. So first, ensemble learning. So in this talk, I'm going to use either a model or a learner to represent any math function that can be trained or tuned to perform a specific task. In particular, if we have a task of classification, then the model or learner is a classifier. If it's for regression, then the models or learner will be regressor. On the other hand, you can also use it for ranking. Then we have the so-called ranking machine. Okay, then how about ensemble? As you can see, we don't pronounce as ensemble, so this is a French word. It means a group of objects. And in this context, in our talk, when we say ensemble, we are trying to combine a set of models in order to reach a better prediction. So the models can be the same as in bagging and boosting, or they can be different types. Then how do you combine models? There are two ways. We can do parallel combination. We can do serial combination. We are going to have more details about that. So what's the advantage of ensemble? What's the advantage of using, say, many classifiers instead of a single one? If you know there's a TV game show of Who Wants to Be a Millionaire, you know, this is a famous TV game show. In the game show, the contestant is given a series of multiple choice questions, and whenever he cannot answer the question, he got two choices. You know, he can, the first one is he can ask the audience, and the audience will input the answer and do a voting. And on the other hand, he can phone a friend to get the answer. But usually, most of the time, when you ask the audience, you can get a correct answer most of the time. So this is the so-called more opinions are better, or the so-called wisdom of the crowd. So here, let's take a look at the ensemble of parallel connection or parallel combination. For instance, assuming we have K models. Let me write here. We have K models. I can denote it as a F1, F2 until Fk. And our prediction, we can write a prediction like this. Y1 is the estimated output from F1. And X is the input vector. And similarly, yk is equal to the prediction of model k. And if we want to do majority vote, then the output will be y hat is equal to the mode of y1 until yk. So when I say mode, that means we are choosing the predicted output that appear the most times in these k models. But on the other hand, we can use weighted majority vote. For instance, if we assume it's a binary classification, so we have a binary output. Binary output could be -1 or +1. So the overall output y hat is a linear combination. Suppose it like this summation alpha j times y j hat, and I range from 1 to k. So this is a linear combination. After the combination, you need to take the sign of the linear combination. So when the linear combination is positive, then the weighted majority vote is +1. On the other hand, it should be -1. And here we have the weights. This is the weights. The weights of each model. And of course, if you have more confidence in a specific model, you can tune up the weight for that model. So this here is a schematic plot. We have input here. We have a committee. Committees of classifier. Then we pass the output into an aggregator. It's either a simple majority vote or weighted majority vote. So this is for parallel connection of ensemble. On the other hand, we can have the so-called serial connection. So we need to train a classifier based on other classifiers' output. For instance, if we have a simple connection like this is a simple serial connection. Then you can write something like this: y1 hat is equal to f1 of x, where x is the input. So we can say y1 hat is here. Then y2 hat is equal to f1 of y1 hat. So we have a y2 hat here. And similarly, we have a y3 hat here. So y3 hat is equal to this should be f2 and f3 y2 hat. So this is a simple serial connection. On the other hand, we can have a mixed mode. We have a parallel connection here and a series connection here. So the output will be, for instance, the y hat will be f of 4, taking the inputs from the outputs of previous model. So it should be y1 hat, y2 hat, y3 hat. So the idea is pretty similar to the idea of multiple layer perceptron, or simple neural network. And it's also very similar to a method that has been proposed long time ago. It's called GMDH. It's called group method of data handling. But here I won't go into details. If you are interested in the details, you can Google either MLP or Google GMDH. And in particular, if the last, when I say top, it should be last. When the last classifier, for instance, this one if this one is linear, then it becomes weighted majority vote because it's taking the input from the previous layer and doing a linear or weighted sum of the outputs from previous layers. So this is a simple introduction to ensembles of serial connection and parallel connection. Now here we have other examples of ensemble. So actually the concept of ensemble is there are a lot of examples in different literatures. We can, for instance, we can call it a mixture of experts. Here the weight can be is actually a crisp interval on x. For instance, taking this graph, this plot as an example, we can write a function. For instance, alpha 1 is right here. See, we can clearly distinguish into three intervals. So we have alpha 1 of x. When x is in this interval, then alpha 1 x is equal to 1, otherwise it's 0. Then we have alpha 2 of x, alpha 3 of x. So the output, for instance, y hat is equal to alpha 1 of x times the linear function. For instance, I would write it as L1 of x plus alpha 2x times L2 of x plus alpha 3x times L3x. So actually we are combining linear regression at different interval in order to create the final output. Then this is called crisp interval because once it's in the interval, the degree of belonging is equal to 1. On the other hand, is equal to 0. Then we can have a fuzzy version of the degree of belonging. It's also called membership function. In this case, alpha 1 is, for instance, it could be a trapezoidal function like this. Then alpha 2 should be another trapezoidal function like this. Alpha 3 is another trapezoidal function. So by using a fuzzy version, we can have a continuous transition, between different models. So this is also examples of ensembles. Okay, so the first one I'm going to talk about ensemble. First approach is bagging. Bagging, the concept is we are going to learn many classifiers instead of a single one. And each classifier can only use a part of the data set for training. Then we can combine the models with voting or averaging. So the idea is it's pretty easy to build a single model. Why don't we build more models for better prediction? So the major goal is to reduce overfitting. Why is that? Because each classifier only sees part of the data. So there's no way, for any classifier to memorize the data because each one of them can only see a portion of the data. So it's getting more, it's getting less likely to overfit the data. So it's basically it's based on the concept of bootstrapping. Bootstrapping is a statistical test or metric that relies on a random subsample of the data with replacement. We can use the concept of bootstrapping to estimate the property of an estimate. When I say estimate, it's like the mean of a distribution of the variance of a distribution. So we can do resampling and measure the mean, and then we eventually can see the deviation from the true mean. So the concept of bagging is based on the concept of bootstrapping. We are going to create a random subset of a data set by resampling. And for instance, in practice, we are going to draw n prime of the original n samples with replacement. So when we are talking about samples, that means we are drawing the data from the approximating distribution. Remember, whenever we have a data set, it's a realization of the distribution. We can never know the true distribution. Instead, we are using the data set to approximate the distribution. So this is the idea of bootstrapping in statistics. So bagging in practice is equal to bootstrapping plus aggregation. In the step of bootstrapping, we are creating a random subset of the original dataset with replacement and using the random subset to train a model. Then in the aggregation part, we are repeating the above process k times to have a k models for aggregation. And then, we can aggregate the k models to get the final output. For aggregation part, especially for classification, we can perform a majority vote or a weighted majority vote. And for regression, we can simply doing an average. And here is a simple illustration. Suppose we have a data set like this. Then suppose this is the true decision boundary. Of course, we don't know where the true decision boundary is. Then we can take a portion of the data. For instance, I take this part of data and create a model like this. This is the model's decision boundary. I take another portion of the data to create another model and its decision boundary. Then I take another one. And by creating many models based on a portion of the data, and after majority vote, hopefully I can recover the true decision boundary, which is right here. This is a true decision boundary. So remember, by taking a portion of the data set, we are trying not to overfit the model. So this is backing. So we need to mention another notion of a bias and a variance trade-off. When you are fitting a model, there are two types of error. One is bias. Bias is the error due to model choice, due to incapability of expressive power of the model. So in order to reduce the bias, we can use models with higher complexity. And on the other hand, we have the variance. Variance is error due to randomness of data. So if we want to improve variance, or if we want to reduce variance, we can use more data for constructing the model. But usually, if we increase the model complexity, then it's likely to run into the situation of overfitting. That means the variance is getting higher. So here we have a plot on the x-axis. This is the model complexity, and the y-axis is the predictive error. And when the model complexity is low, then we have a high bias along this interval. And on the other hand, if the model complexity is high, then we have the error due to this region, high variance. So usually we need to find a balance between high bias and the high variance. So this is any question? Okay, so in order to plot this bias variance trade-off, one thing we can do is to do cross validation. And cross validation is a way to estimate the true error. Remember, we are trying to estimate because we don't know the underlying distribution, so we can only use data to estimate the true error for model selection. So the process of k-fold cross-validation is like this. You split the dataset into k parts, and using k-1 parts for model construction and 1 part for validation. And you can do a rotation and repeat k times to construct k classifier to estimate the training and the validation error. Then we are using the validation error as the estimate for the true error for the underlying distribution. So once you have the k classifier, one thing you can do is to simply combine them into a super classifier. So actually this is using the idea of bagging, simply to combine all the classifier into a better one. So if you are doing cross validation, then you plot this is a model complexity, and here is a validation error. Then usually we can see a curve like this. Initially it's going down because the bias is getting improved, and later on it will be going up. This is for validation. But if you are plotting the same curve for training error, the training error will be usually is slightly lower than the validation error, and it will be going down all the way. So the important things we need to remember is we need to cut off at this point. So this is the optimal complexity of the model. You need to choose from a series of model of different complexity. So by using cross validation, you can simply draw the line of variance and bias and the variance to have curve like this. So here is a comparison for different strategies for reducing overfitting. Once we reduce the likelihood of overfitting, then on the other hand, we are improving the model's generalization capability. That means whenever we have unseen data, then the model should be predict, as close as possible of the seen training data. And for bagging, we are using drop data for reducing overfitting. And if you know deep neural network, here we can use the dropout rate to control the ways to drop out, and then it can serve the same purpose to reduce overfitting. And in general, we can add regularization terms, to control the model complexity in order to reduce the likelihood of overfitting. So here we have 3 different strategies for reducing overfitting. In particular, when we talk about XGBoost, so we need to put a regularization term into the objective function in order to control the complexity of the boosting trees. Okay, let's take a look at the decision tree. Here I'm using, originally it's called classification and regression tree. So this acronym is CART. But sometimes we refer to it as decision trees. Sometimes we refer to it as a regression tree, but they are actually pretty much the same thing. So this is a simple example of a decision tree right here. And the decision, the prediction is does the person like computer games, or the degree a given person like computer games. And we have, for instance, 5 entries of training data. And the decision is like this: if the age is smaller than 15, then we are going to the left subtree. On the other hand, if age is greater than 15, then we go to the other side. And for this diff node, we are given a score of the prediction. For instance, if the age is larger than 15, then the score is -1. That means the guy is not likely to play computer games. And once you reach this is another decision node. So internal node is for decision. If it's male, so the degree this guy like to play computer game is +2, or if it's female, then it's plus or 1. So the external node for each external node is the score of a class. So actually we are putting all the instances here for instance, here we have 5 instances, x1, x2, x3, x4, x5. Then eventually this instance will be distributed into into each leaf of them, and each leaf represents the score or the class for classification or the value for regression. So this is the basic idea of decision tree. So you can, given a set of data, you can use tree induction method to derive the tree efficiently. But here I won't go into detail because this is pretty much basic. You can find a lot of tutorial on tree induction on either Google or on either document. So here we want to use the trick of bagging for trees. Usually, how do we do this? Initially, suppose we have a table. This is our training data. Usually, this is the entry. For instance, entry 1, entry 2 of your training data. This is the fields or column. We have this is first column, second column. This is called features. And usually the number of data is bigger than the number of features. So the plus should be like this to represent the the real situation. So the number of data is usually much larger than the number of features. Initially, when we were talking about bagging, we are talking about we can take a random sample from the training set. That means we can drop some of the entry right here. We can drop, for instance, this entry, drop this entry, or select this entry for training a model. But for random forest, we are training the classifier based on a subset of features. For instance, suppose there are 10 features right here. 10 features. We can select 9 features to build up a decision tree, and then we can do something like cross validation. We can rotate on the deleted features and select 9 features each time, and eventually we can train 10 different trees, and we can aggregate the output of the trees. So this is called random forest. The idea is pretty simple. So the good thing is all the advantage of decision tree can be inherited in random forest, and it's pretty efficient because the tree induction is pretty efficient. And on the other hand, it has the advantage of bagging because each classifier can only see a portion of the features of the data set. So this is called random forest, and it has been a very popular paradigms for machine learning, and it can be also used for either classification or regression. So here we have a summary of bagging. So bagging stands for bootstrap aggregation, and it can because you are using a simple weighted average or majority vote, so the complexity of the model can be kept down, and it plays on variance and bias trade-off. When you are doing the averaging, actually you are reducing the variance of the bias variance curve. And its strength is you can get better generalization. And for coding part, it's pretty easy. All you need to do is do a subsampling of the data set and construct the model as usual, and then combine them by majority vote. But the weakness, of course, is the cost you need to pay is more computation. So here we have a reference. We have a simple concept right here, and here we have some illustration. I'll send, this is an updated version of my slide. I'll send it to Norman later. Okay, next we are going to take a look at boosting. For boosting, the idea is similar. We want to build a sequence of classifier. And early classifier, it should be pretty simple classifier. Then it bounds to have some hard example that is hard to learn or that is misclassified. And the later classifier trying to get those hard example correct by adding new classifier. Usually the classifier is the so-called weak classifier. By combining all the weak classifier, eventually we are hoping that we can end up in a strong classifier. So why do we need to use a weak classifier? Because we want to be able to derive the classifier in an efficient manner. So this is the concept of boosting. So here we have some example of boosting. For instance, ADA boost, which is used for face detection for many years. And we have a Brown boost, logic boost, and a gradient boost. We are going to spend more time on gradient boosting. So gradient boosting is simply a gradient descent plus boosting, and it's good for either classification, regression, or for ranking. And the concept is again pretty simple. We want to train a set of models sequentially, one by one, or this is called stage-wise. At each stage, you are going to create a additional new classifier and add it to the pool of classifier. Then the overall model is the collection of the simple classifier you have built so far. So the overall model is progressively accurate, and but again, it's progressively getting complicated. So here I'm going to give you a simple example here. The steps in boosting. First, you need to train a model like here, and you compute the error. Then you train another model based on this error. You want to predict the error. And once you have done training, you need to add this model to the original model. So you are going to have a collection of model, and the number of model is getting bigger and bigger. And hopefully the error is getting smaller and smaller. So this is the basic step. Here I'm going to use a simple example to show you the operation of boosting. This is a regression example. We have the data in red, and our weak regressor or weak model is called decision stump. It's a one-level decision tree. Here we have a simple example right here. It's a single. We have a single internal node. So this is a leaf. It's based on a single split. This is for iris data recognition. If the petal width is greater than 1.75, then it's one species of the iris data. On the other hand, it's another species. This is a very simple classifier, or you can call it a threshold classifier. So it's called decision stump. For instance, for this data set, we can create a simple decision stump like this. This is the threshold. On the left side, the output is 0. On the right side, the output is another value. So once you have the prediction, and then you have the error residual like this, then we put out the error residual as the training data for another decision stump. Then for here, you can see if you want to fit this error residual, so the decision stump will be something like this. So you add this model. Here we have two models here. If you put them all together, you get a new model like this. Then we have another error residual, and then we can fit another model right here, maybe like this one. Then we add this model to the one here. We add this one and this one to get a new model. So we are adding more and more models to predict the error. And the overall goal is to reduce the residuals or reduce the error function. So this is a simple example of boosting. But remember, when you are using boosting for this type, you are not allowed to use a linear regression. Because if you are using linear regression, all the combination of the linear model is still a linear model. So you are not increasing the predicting power of the overall model. So usually we need to use non-linear regressor, like the decision stump right here. Okay, so what is gradient boosting? Of course, here we need to talk a little bit about gradient descent. And the concept is pretty simple. Suppose you have an objective function like this, j of theta, and the theta is function. Then if you want to use gradient descent to minimize this function, uh, so the update amount, let me write delta theta here, will be equal to the negative gradient. So we use minus eta times the gradient of theta. So eta here is usually called step size or learning rate. So if you plot the contour of the objective function, so at this position, this is theta, then we are projecting, the negative gradient will be like this, along this direction, along this direction, along this direction. So it can be proved that the gradient path will be perpendicular to the contour. So this is a gradient descent, or you can write theta next will be equal to theta now minus eta times the gradient. So this is gradient descent. So how this is related to boosting? How come gradient boosting? In gradient boosting, we can combine gradient descent and the boosting. So we need to give more detail here. Suppose we have a data set like this. We have n samples from the data set. And suppose our current model is f of x. This is our current model. Then the estimated output we can write it as a y hat is equal to, for data point I is equal to f of xi. We can plug in the data entry of xi to get the estimate of the output. And the objective function we want to minimize can be written as j. I use j to represent the objective function. We can use a simple square loss or sum of square error is a summation over I equal 1 to n, then yi, this is the true output, minus the estimated output, and put a square here. And usually for simplicity of mathematic derivation, we divide it by 2. So this is our objective function. I'm collecting the deviation between the design output and the estimated output, and compute the deviation, square it, and do a summation. So in order to find, we want to update this function in order to do a better prediction. So we can view y hat I as a independent parameter. So we can find the gradient. Partial j over partial yi hat will be equal to yi minus yi hat, and because of chain rule, we need to find the derivative of minus yi hat to itself. So we are going to multiply this by minus 1. So this is equal to minus yi minus yi hat. And this is the so-called residual, or the deviation between the predicted and the actual output. And here we can see it's actually equal to the residual here is equal to negative gradient. Because we can put a minus sign here to here. So the residual is equal to the negative gradient. So then it's become very interesting. We want to update f of x. So if we use this negative gradient, so the update formula of f xy will be like this: f new, I'm going to have a new of xi is equal to f of xi. This is the older one, plus learning rate times the gradient yi minus yi hat. So as long as we can, use a function to approximate the negative gradient, then we can update the function f in order to achieve a better prediction. So in other words, we can fit another function. We can fit h of x hat to approximate the residual or the negative gradient. So yi minus yi hat. Fit f of h of xy. We need to find this function to approximate the negative gradient. So this is the basic idea of gradient boosting, because we need to eventually we need to find another model to approximate the residual. But in this case, the residual is equal to the negative gradient when we are using square laws of the so-called sum of square error. I hope this is clear to you, but this is based on simple math derivation. You can try by yourself. By the way, I am doing the recording, so I can send the recording to Norman if you are interested in see the record again. So, so how come the gradient descent is related? Here I'm give you a recap. The residual is equal to the negative gradient. So we can use the residual to fit another function or another simple model, h of x, to fit h of x to residual is equivalent to fit h of x to negative gradient. So we can update the original model based on residual, or it's equivalent to update the original model based on negative gradient. So in this context, we are actually performing, gradient descent. That's why it's called gradient boosting. Then if you take a step back, we are trying to find f of x, trying to find the model f of xi, and the residual is minus yi. This is the residual. Then we want to update our model by adding another function, plus h of xi plus yi. Oh, sorry, minus y. So h of xi is used to fit yi minus f of xi. So if we can use h of xi to approximate yi minus f of xi, then the residual will become 0. So then we are done. So the concept is pretty simple. Then how come we want to take all the trouble to make it, in the context of gradient descent? The main reason is we want to, be able to take care of other different objective function in the same manner. So let me show you. Okay, this is again a recap of gradient boosting for regression with sum of square error or square roots. So you have the sum of square error like this. Then again, this is your input part of your training data. This is output part of the training data. Then the negative gradient is equal to, the derivative of partial j with respect to partial f of xi, and turn out it is equal to the residual. So the step in gradient boosting is we can start with the initial model. Initial model is like this, is only an average. And we can calculate the negative gradient. And for square loss, the negative gradient is equal to the residual right here. Then we can fit a regressor h of x to the negative gradient. Then so the model update is like this. So once we can fit h of x to the negative gradient, and we incorporate it into the set of model by multiply it by a learning rate or step size. Usually we put it as 1 here. Of course, you can do further optimization to find the optimal value of low, but usually we don't bother to do that. But as I say, we want to formulate in the context of gradient descent because we can choose any format of the objective function. Here we have a list of several objective functions. We can use a square error or sum of square error. This is called square loss, and we can use another one. It's called absolute loss or Huber loss. And the most common one is, of course, is square loss. It's mathematical, tractable. It's used pretty often, but the bad thing about square loss is it's very sensitive to outlier. I'm going to give you an example right here. And for absolute loss is more robust to outlier, and Huber loss is even more robust to outlier. Here I'm going to give you an example of one-dimensional regression. We have f of xi right here, and this is the yi, and this is a prediction, and this is the design value. And if we compute the square loss, then this is the outlier. So for the outlier part, the square loss, you can see there is a large value for the square loss for the outlier. So this is no good because the model will pay much more attention on correcting this data. So you are putting more energy on correcting outlier. And for other data set, for normal data set, then the fitting will be suffered. On the other hand, if we are using the absolute loss, then you can see the contribution of the outlier is less. Similarly, for Huber loss, the contribution for the outlier is lost. So the fitting will be more balanced on both normal data and the outlier. So that's why we introduced the concept of gradient descent. then we can take care of any kind of objective function in a boosting algorithm. So here we have the procedure. If you have a general loss function, then how do you do gradient boosting? Again, because it's a general function, so the general function is represented by the deviation between the design output and the predicted output, and it's represented by a function of L. Then we can compute the negative gradient. So on this, we can have a specific format of L. Then once we defined L, then we can compute the negative gradient. So we are using h of x to fit it to the negative gradient, which is represented by minus gx in a general format like this. So all the other steps remain the same. So here we have a summary here. By following the negative gradient instead of the residual, then the model will pay less attention to outliers. So this is the advantage of using other loss function, which is more robust to outliers. And by using the concept of gradient descent, we can take care of any any format of loss function. So here we have a summary of gradient boosting. The summary is like this. We can fit an additive model in a forward stage-wise manner. And in each stage, we are going to introduce a new model to improve the existing model by following the negative gradient. And we can use any kind of differentiable loss function. And again, here we have some reference right here. So we have finished the part of gradient boosting. Now let's get back to the decision tree, the strengths and the weakness, because we are going to use decision tree, for once it's for backing, then it's like then it's the paradigm of random forest. Then we can use for gradient boosting. And the next time we are going to use the decision tree for to be used in the so-called XGBoost. The strength of decision tree is easy to comprehend. The concept is pretty simple, very fast for train, and it's a nonlinear model. So you can combine many decision tree to create an even more nonlinear model, which you cannot achieve by using a linear model. And it's invariant to feature scaling, so you don't need to do all kinds of feature normalization. And it's pretty robust to feature type. Either it's a numerical type or categorical type. You can do decision tree induction. And even you have a correlative feature, it can select the best feature for you. And if even you have a missing value in the data, it has some specific way to handle missing value. But about its weakness, the accuracy is usually not as good as, for instance, SVM. And if there are linear relationship, it's very inefficient to fit linear relationship. So how do you improve decision tree? Again, we are talking about ensemble, using a set of decision tree to create a better predictor or a better model. We were talking about random forest, so it's based on backing. You feed a set of tree on different samples of the data and take the average. Then the good thing about this is parallel in nature, so you can use GPU computation to speed up the whole process. For gradient boosting, again, it's based on gradient descent and boosting, so it's based on boosting. So you feed a sequence of tree, and each try to reduce the error from prior trees, and it's cascaded structure or serial connection. So it's cascaded in nature, so it's harder for parallel processing. So here I'm going to give you a simple example of tree ensemble. So we have a tree 1 here, we have a tree 2 here, the second tree. So again, it's based on the decision of either a person like computer game or not. So if you send the input instance, here we have 5 instance here. If you send this little boy, and the output is +2 for tree 1, plus 0.9 for tree 2, so the final output is the summation of these two. On the other hand, if you send the input as I think this is a grandpa. You send a grandpa here, then for tree 1 is -1, for tree 2 is -0.9. So again, you add the output of each tree to get the final output. So this is the example of tree ensemble. Then how do you derive a sequence of tree to reduce the error? Here we give more characteristics of tree ensemble. First, you need to notice the fact almost half of data mining or machine learning computation are won by using some variant of tree ensemble. So it's amazing to see by using a sequence of trees, it can perform much better than all the other classifiers. So the advantage of tree ensemble, all advantage of decision tree are inherited, from the constituent decision tree, and of course it's ensemble, so we can achieve better accuracy, and it can learn high order interaction, and it can be scalable if the code is implemented carefully and correctly, and is used practically in industry because of the fact it's a winning algorithm for many different competitions. So for the remaining about 20 minutes, I'm going to talk about XGBoost. It stands for Extreme Gradient Boosting. Again, the concept is based on gradient boosting, but so it's tree boosting, but here we are going to try to add a regularization term in order to cap the complexity of the model to be a small number. So it's getting popular because here we have some words from the the website right here. It supports multiple language like C, C++, Java, Node.js, so on and so forth, and different platform. And it can be distributed on various clouds such as AWS or Microsoft Azure. And it has wins many ML competition and highly scalable. So I got this information from Google. So in the year 2015, 17 out of 29 Kaggle champion actually use XGBoost in their solution. So this is quite an amazing achievement of XGBoost. So here we want to visit the objective function that is used almost everywhere for machine learning. So the objective function can be defined as a training loss here, right here, and the regularization. For the training loss, we are trying to measure how good the model is fitted on the training data. For regularization, we want to measure the complexity of model. We want to keep both terms as small as possible. That means the prediction error should be small, and the model complexity should be small too. And again, we have a different kind of loss function and a different kind of regularization term. And here I won't go into details. So for boosting, we want to learn a sequence of tree. So the final output is equal to the summation of a sequence of tree, and each of the tree is coming from the the space of function containing all regression trees. So we want to the parameter in our tree, we want to include the structure of the tree and the parameter in the leaf. Then we want to use the function as parameters. So we are, instead of learning weights in a multi-dimensional space, actually we are learning function of trees. So this is a very different from traditional machine learning. For instance, like a neural network, we are only adjusting the weights, but here we want to adjust both of the parameter and the structure of the model. So here again, this is the assuming we have k trees. This is the estimated output given the input part of the data set xi. Usually this is a vector. And our objective function, again, we put it into two parts. The first part is training error. We use a general loss function here, and this is the complexity of the tree right here. And there are many ways to define the complexity omega of the tree. And we are going to have a more detail later. So this is our objective function. So it's hard to use statistical gradient descent because we are not only optimize the parameter, we are going to find the tree and choose the base structure for the tree. And again, we are going to use additive training or the so-called boosting. Initially, we are going to have a simple model. It's all equal to 0, and we are adding, in the second iteration, we are going to add one model of F1. And in the second iteration, we are going to add the second model. And for the iteration at time t, we have the older model right here. It's the only summation of the previous trees. And we are going to add a new model right here. So this is a new function. So here, this part is all the function added in the previous round. So it becomes very straightforward. We want to find this function to optimize the objective function. Or find this tree, actually this is a tree, to optimize the objective function. Here, as I say, objective function. So at iteration t or time t or round t, the output is equal to the previous model plus a new model. This is what we want to decide in iteration t. And we plug in the current model here into this objective function right here. And then if it's a square loss, then it's pretty simple because this part can be written here as yi minus yi hat t minus 1 plus ft of xi. Sorry, this should be a minus. And take it to the square. So it's equal to yi minus yi hat t minus 1 square. So actually this is a constant. So we can eliminate this guy. And plus another 2 term right here. And then we put all the other constant right here. So this is called right here. This is a residual from previous iteration or from previous iteration or from previous round. But it's still pretty complicated. You know, if given a general loss function L here, how do you optimize it? So we can use Taylor expansion of the objective function. Remember Taylor expansion f of x plus delta f is equal to f of x plus the first derivative times delta x plus the second derivative of f at x times the delta x squared. So if we can define gi as the first derivative and hi as the second derivative, then the objective function will be written like this. And again, this is constant. We don't need to consider this guy. Of course, if you think this is complicated, you can always fall back to the square laws to verify you understand the formula. So this is the objective function we want to minimize. And remember, it's a summation over all the data instance. Now we want to change the summation from over all the data instance to the summation over all the leaves in a tree. So we can define a function w. Actually, w is the weight or the score in the leaf. And then w is a, t element vector, where capital T is the number of leaves. And so it's pretty easy to here is an example of Q of x. Q of x indicate when given an instance of x, where is the corresponding leaf the instance will reside. So for instance, for this little boy, because it's been put into the first leaf right here, so Q of this guy is equal to 1. So because this is leaf 1. And Q of our grandma, because it's in leaf 3, so Q of grandma is equal to 3. So for any given instance, we can find the leaf, the index of leaf, the instance will be put into. Then we can define the tree complexity. So one easy way to do this is for given a tree like this, omega of this tree is equal to gamma times the number of leaves plus 0.5 times lambda of the sum of the square weight or square score. So this is we are putting the penalty on the number of leaves. We are putting the penalty on the magnitude of W. So if omega is small, that means the number of leaves is small and the weight has been kept small. So for instance here, for this tree, omega is equal to gamma times 3 because we have 1, 2, 3 leaves. And plus 0.5 times lambda. And 4 is the square of 2 right here. And 0.1, the square of 0.1 is 0.01, and the square of -1 is 1. So this is a penalty of this tree. So next we are going to introduce the instance set in a given leaf index J. By using this notation, here the original objective function is the summation over all instances. Remember, we have a x1, x2 until xn. We have so many instances here. So this is a summation over instance. Then when we distribute all the instances into the leaves of the tree, then we can rewrite the objective function as a summation over the instance in the leaves. Then by doing this kind of rearrangement, then we can find actually this is the summation of t independent quadratic function. So once it's a independent quadratic function, then you can solve the quadratic function directly. So that's the beauty, right here is the beauty of XGBoost. So once we have the quadratic function, we know how to optimize the quadratic function. Then we can define, we can further simplify the objective function. And for a given structure of tree, when the structure is fixed, then we can find the optimal weights in each leaf and the resulting objective value. So since it's a combination of t quadratic function, it's pretty easy to do so. So in other words, we can, for a given tree structure, we can find the objective function. But here I won't go through the example right here because we don't have too much time. And if you are interested, you can go through the details by yourself. And then in order, we want to search a single tree which can optimize the objective function. One way to do this, we can enumerate all the possible tree structures. And then once we have lambda and gamma, we can have the objective function. And then we can find the minimizing weight for the tree. But then there are infinite number of trees structure to optimize. So again, we are using the concept of tree induction. And for tree induction is based on a greedy search. We can start from tree with depth 0. And for each leaf node, we can find the best variable to split. And the change, after we have done the split, is called gain, or the so-called information gain. We want to find a split that can generate the highest gain. So we can do a enumerate on the feature in order to find a split in order to get the maximal gain. Then how do we find the best split? Again, it's pretty straightforward. We can, put all the instances based on the sorted by the feature value, and we can, if there's a split over here, we can find compute GL and the GR, then we can compute the gain pretty efficiently. So we can simply do a linear scan. Once all the instance is sorted based on a given feature, we can do the linear scan to find the best split. So here we are pretty much done with the whole algorithm of XGBoost, and here is the algorithm of finding the best split, and here is the time complexity of growing a tree of depth k. But here again, I won't go into details. So this is a recap for XGBoost or boosted tree algorithm. We want to add a new tree at each iteration. So for at the beginning of each iteration, we want to find the first derivative, the second derivative based on a given loss function. It can be any kind of loss function as long as it's differentiable. Then we can use a greedy search to grow a tree, and in order to optimize the objective function. So once you find the tree to be included in the collection, we can put a small learning rate here, and this is eta is called step size, or learning rate, and usually it's set to be around 0.5, which means we are not doing fully optimization in each step, because we can reserve some room for improvement in the future run. So by doing this, it can help us to eliminate the possibility, to reduce the possibility of overfitting. Okay, let's come to the conclusion part. So nowadays we are most of us are working on the modeling on big data. So the number of samples is usually huge, and the dimension is pretty high. So here we have two successful paradigm of modeling. The first one is a deep neural network. The second one is boosting. Here, for deep neural network, usually the training is pretty slow, but it's pretty good for image classification. Especially there's a image cup, and most of the big company they are submitting their algorithm. And for instance, Google has some winning model for ImageNet, and they also release their weights, so we can use transfer learning. You know, if you have a specific task, you can take the weights from Google's net, and you can jumpstart your training. Usually, the training time is shorter, and the accuracy is higher. On the other hand, you can build the overall model iteratively, and each step you are adding a simple model for face training. So this is boosting. It's usually much faster than deep neural network or convolutional neural network, and it's good for non-image application. So it's trainable for text prediction, but there's no way to do transfer learning because there's no existing model. So this is a simple comparison between two of the successful paradigm for modeling of big data. So I guess I'm pretty much done here. We have some reference about boosted tree, and especially this is a homepage for XGBoost. There are a lot of information, including tutorial codes and all the comments from the user. Okay, and here is some, some explanation from the Kaggle winner who is using XGBoost for the competition. Okay, I think I'm pretty much done here. Thank you very much. I'm welcoming you to have, if you have any question, I'm happy to answer.